Hello and welcome to Sean White's Solar and Energy Storage Podcast. In this podcast, we're going to compare different things about different battery technologies. We're going to cover what makes different battery technologies better for different applications, looking at primary and secondary batteries, state of charge, that's SOC, versus depth of discharge, that's DOD. We're going to talk about voltage versus charge, battery open circuit voltage, battery internal resistances, lithium versus lead acid, battery nominal voltages, such as your typical lithium-ion battery, which has a nominal voltage of 3.6 volts, your LiFePO or your lithium iron phosphate battery, which has a nominal voltage of 3.2 volts, and your lead acid batteries, which have nominal voltages of 2 volts per cell. Then we're going to talk about cycle life factors, that's cycling your battery up and down, energy per weight, energy per volume, power per weight versus energy per weight, arbitrage, self-consumption, maximum discharge current versus continuous current. There is a difference. Charge voltage versus nominal voltage versus float voltage. You don't want to float those lithium-ion batteries though, just your lead-acid batteries. BMS, that's battery management systems, algorithms, nickel metal hydride, NiCads, and recycling batteries. And if you want to learn more, go to solarsean.com. Now, on with the show. Ladies and gentlemen, we're going to talk about different definitions about batteries in general, and we're going to end up talking about specific things about lithium-ion batteries. That's what most of you are probably interested in because that's what the market is doing these days. It's going lithium. Now let's get into some definitions. We're going to talk about different things like battery classifications. So not all batteries are created equal. They're not like people because all people are created equal, except for people that you don't like. Hey, they forgot to put that in the Constitution. So even batteries with the same chemistry can have differences because you make a little thing a little bit better for one thing and a little bit worse for another. Oftentimes there's a trade-off, for example, for making a battery better for power, that's letting it all out at once, versus energy, that's how much energy you can store in there. And we're talking about energy storage systems, so that's important. So we can have them high power or high energy oftentimes, but not both. If you want a high energy battery, think of a lot of connections and bigger wires and things like that. Bigger things that conduct electricity. Other classifications that we can see could be high durability, and that high durability can also be at the expense of power and energy. Little refresher here, secondary battery means rechargeable, primary is not rechargeable. The state of charge of a battery is how much capacity is left in the battery. So if you drain it all the way down to nothing, that's a zero state of charge, not too good for the battery. A lot of times people like to charge their EV batteries, if they're not going to drive too far the next day, up to an 80% state of charge because it's more healthy for a lithium battery not to get fully charged. With a lead acid battery, it is not healthy to leave a battery at 80% state of charge. It's healthy to charge it fully to 100% and even trickle charge it over that. With lithium batteries, you do not trickle charge because you could end up with a thermal event. Thermal event is another word sometimes for fire. The depth of discharge is the opposite of state of charge. So if you added the state of charge to the depth of discharge, you should always get 100%. So if you are at 0% depth of discharge, that means you're fully 100% state of charge. If you're 100% depth of discharge, that means you're at 0% state of charge. And a lot of times you'll just see it abbreviated with the TLA. That's the 3-letter acronym of depth of discharge is DOD, and the state of charge is SOC. They're pretty much talking about the same thing. If you know one, you could figure out the other. Now the terminal voltage, that's just the difference in voltage. Voltage is a potential difference from one terminal to the other. And the terminal voltage will vary depending on how charged your battery is. So a charged battery has a higher voltage than a discharged battery. However, it's not related in a linear fashion. That means if you had a 12-volt battery and it was 6 volts, you don't have half of your energy there. You have nothing. Open circuit voltage just means the voltage when something is off. So your open circuit voltage is higher than the voltage when you have a load on it, but it would be lower than the voltage when you're charging the battery. Your charging voltage would be higher than your open circuit voltage, and your open circuit voltage would be higher than your voltage with a load on it. But if you measure the open circuit voltage, that can tell you the state of charge. And a lot of times we'll see different tables that it's showing you the state of charge. Just remember that state of charge, when they're saying how charged the battery is, does not mean that that chart will be accurate when there's a load on it or when you're charging the battery. When you're charging the battery, the voltage will be higher. When you're discharging the battery, the voltage will be lower. And the open circuit voltage will change depending on how charged or discharged that battery is. So that would be your state of charge, and your depth of discharge will affect your open circuit voltage. A lot of times you'll see charts or tables that are showing you that. So inside of a battery, you have some internal resistance. Resistance means heat. That internal resistance can depending on the state of charge, the technology of the battery, and how fast and slow you're charging the battery. This internal resistance can cause heat. And as your internal resistance increases, the battery efficiency decreases and the thermal stability is reduced. That's why, especially with lithium batteries, you need to have temperature sensors in there and a battery management system to know exactly what's going on. Lithium batteries have a lot less internal resistance than, say, a lead acid battery or even your flashlight battery. Your flashlight battery, if you short it out, it's not going to explode as bad or at all compared to a lithium battery. If you short that out, you can have a bad day. Nominal voltage is just the normal voltage of the battery, or the voltage that we just say that the battery is in name only. So some people say nominal means in name only. Most of the lithium batteries that we're dealing with have a nominal voltage of 3.6 volts, except for the lithium iron phosphate, it's 3.2 volts. And for a lead acid battery, the nominal voltage is 2 volts. However, as I said before, the voltage will go higher and lower than the nominal voltage. The cutoff voltage of a battery is typically going to be when your battery gets to a voltage where that's empty, or whatever you programmed it for. You'll program it for the cutoff voltage. You don't want to ever take your battery down to zero. Not a good thing. So let's look at this definition. And remember, in different places, you might find different definitions. If you're talking about somebody who's more science-based in the lab versus somebody that's more in the field. But here we're talking about capacity or nominal capacity, and this is going to be in amp hours given for a specific C rate. Sometimes you hear the word coulomb. So there's a guy named Coulomb, and a coulomb is a whole ton of electrons. It's the amount of electrons in 1 second for 1 amp. And the coulometric capacity, that's going to be measured in amp hours, is going at a particular C rate from 100% state of charge to the cutoff voltage. So what is the cutoff voltage? That would be the question. Some people would say 50% state of charge, but then that would give you half of what some people would call the state of charge. So that's why you're going to have some different definitions there. Is the cutoff voltage something that you can program, or when you're going down to nothing left in that battery at all? Just different definitions there. Try not to get too confused, because everybody's confused depending on what your source is for some of this information. The capacity of a battery is typically measured in amp hours. However, sometimes people talk about the capacity of the battery being measured in energy or watt hours when you're talking about an energy storage system. And then other times you hear about capacity when somebody's connecting to the grid is what's the maximum amount of power. So capacity is a term that's used in different ways for different reasons. Typically, though, when you are talking about batteries in the energy storage industry, if you're talking about the battery or the cell especially, you're talking about amp hours. So if you take amps times hours, that's amp hours. And your amp hours are going to be different when you have more hours because you're discharging it slower, and it's more efficient that way. You're making less heat. And a lot of that could have to do with the internal resistance of the battery. And there's more internal resistance in a lead acid battery than your typical lithium battery. With this definition, we're talking about energy or nominal energy for a battery, and that would also be at a specified C rate, because if you charge it and discharge it faster, you get less out of it. You get less amp hours, you get less energy. So just remember, energy is power times time. Another thing that you'll oftentimes see with batteries is they talk about the cycle life, and that might be specific for specific factors. Sometimes people say depth of discharge when they're talking about lead acid batteries. However, with lithium batteries, if you top it off every day too, that's not as good for it. And another thing too that can mess up your cycle life with a lithium battery is fast charging and fast discharging. And that can also affect the number of cycles for lead acid batteries. So there's a lot of different things that make a warranty for a battery complicated. One of the things about lithium batteries though is you have a battery management system. So the warranty can be checked because there's a computer associated with your battery, and a lot of times it's even connected to the internet, and the battery manufacturer can see if you did something that was bad for your battery. With lead acid batteries, it's harder to check on things like that because the lead acid battery doesn't have a computer in it. The lead acid battery, just kind of think of that as it's kind of slower, so it's less likely to blow up. So you don't need to have all these electronics keeping its eye on it. However, even with a lead acid battery, if you short it out, it can kill you. So don't short out battery cells. If you have a battery management system though, or some internal fusing, that can help you a lot. For instance, I bought a Tesla battery off of eBay. It was just an 18650 cell. And as I was measuring the voltage on that battery, just like I do with a flashlight battery, I shorted it out, and that was quite a spark. So be careful. In fact, be more careful than I was. You're not going to get killed by shorting out a flashlight battery, unless it's a lithium flashlight battery, but you could get yourself in a lot of trouble by shorting out just a single lithium battery cell. So some of the things that have to do with cycling a battery is the higher the depth of discharge, the lower the cycle life. And a lot of times you'll see that in the warranty. The specific energy of a battery is going to be measured in energy per weight. So specific energy is energy per weight. That's what's really important for electric vehicles because you're moving around. You need to accelerate and decelerate. You don't want to have a lot of weight. That's more important than volume, which is energy density. And a lot of times people say energy density when they mean specific energy. And I mean a lot of times like more than half the time. So if somebody says energy density, usually they mean specific energy. And now same thing, we're talking about specific power. And so that's also going to be power per weight. So some batteries are designed for power, some are designed for energy. If you have a grid connected battery, if you're trying to do frequency regulation, you'd probably be more interested in having a battery that had more specific power. And if you're going to do arbitrage or self-consumption, where you're going to hold on to some energy and release it later, then you would be more interested in specific energy. And those examples I just gave you for specific energy and specific power, that would also have to do with energy density and power density. So energy density is going to be energy per volume. And when we're talking about electronics, things that we're trying to fit in our pockets, we often don't care about that extra ounce. We care about it fitting in our pocket. Remember those old cell phones that had lead acid batteries in them? I remember my grandpa had one, and that was not very good energy density. Energy density, just remember, is energy per volume, not energy per weight. And the same goes with power density. Power density is power per volume, not power per weight. And when you're talking about electric vehicles, the important thing is specific power, specific energy. And when you're talking about an energy storage system, it's up to you what you want to be important, how much room you have. A lot of times it's not as crucial as it is with an electric vehicle. You can take up more space on some land. It's not the end of the world. But it is nice to be able to fit a lot of batteries into a container. And that would have to do with your density. It's how many you could fit into a container. So now for the battery, another parameter we're going to look at is the maximum continuous discharge current. And that's just the maximum current that you can let out for a continuous period of time. In the National Electrical Code, continuous means 3 hours or more. That's how we size our wires. Another thing, though, to look at is the maximum 30-second discharge pulse current. So how much current that you can give out over a shorter time before things have time to heat up is going to be more than how much current you can give out over a longer time. This maximum discharge current just doesn't have enough time to heat up your batteries and your wires, just if you're going to have a 30-second pulse of current. And so a lot of times that would have to do with your acceleration in an electric vehicle, but it could also have to do in an electric vehicle or even a hybrid vehicle with your regenerative braking. That's charging the battery as you're going down a steep hill, especially with hybrids because their batteries are way smaller than EV batteries. And if you're talking about your energy storage system here with your pulse current, A lot of times when you turn something on, you need a little bit extra current for a shorter time. Let's say your air conditioner kicks on in your house. It would need more current for a shorter time. And so your energy storage system will usually supply extra current for short periods of time to help you get that thing kicking. When you turn on a motor or a lot of things, it just takes a lot of current just to get it started. And it can be a lot less than 30 seconds. So the charge voltage could be different for different technologies. This could be very different. There's all kinds of different stages of charging. But the charge voltage is the voltage that the battery is charged to when charged to full capacity. So this will be greater than your nominal voltage. That is your fully charged voltage. And now a float voltage, that's typically a lead acid battery term there, because with a lead acid battery, you could still trickle charge it or float charge it. And that means you're at 100% state of charge, and then you're just giving it a little bit extra. It's healthy for a lead acid battery. It's bad to do this for a lithium battery. That's why you can't just swap lithium for lead acid and have your lithium battery work properly. However, with lithium iron phosphate, it can be done without an explosion, but it's just not good for the life of the battery. So you don't want to float charge lithium batteries. You just do that for lead acid batteries. And most of us are dealing with lithium ion batteries. So when you're first charging a battery, there's different stages of charging. Some people will call it a bulk charge. But when you're charging up to, say, 70% or 80%, that would be your fast charging. So if you have an electric vehicle and you're in a hurry and you stop for a cup of coffee, you give it a fast charge, but you don't fully charge it with that fast charge. You just get it up to, say, 70 or 80%. Then you're on your way. It can take twice as long or even longer to get it fully up to 100% because you need to slow down that charge. So maximum internal resistance, sometimes you hear about that, and that's the resistance within the battery. And that can be different for charging and discharging, and that could be your limit of how fast you can charge and discharge a battery. So let's talk about charging and discharging of lithium-ion batteries. It's a lot more complicated than a lead-acid battery. You're going to have battery management systems, different ways to control the charge, and other dangers. But fortunately, our computers are so good that people are not blowing themselves up. And when people compare lithium-ion batteries to gasoline or some kind of fossil fuel or nuclear energy, it seems to be a lot safer. So lithium-ion batteries, one reason why they're so good is they have the higher voltage per cell. Remember, voltage times amp hours equals your energy. So we have volts times amp hours equals watt hours. Lithium-ion batteries have a lot more watt hours per weight or per volume. And so watt hours per weight is called specific energy, and watt hours per volume is called energy density. Another thing also about charging and discharging of these lithium-ion batteries is there's tighter tolerances on detecting a full charge. And once charged, they do not need to be trickle or float charged. In fact, it's bad and could be even dangerous to trickle or float charge a lithium-ion battery. That's why we need a battery management system. And lithium battery technology is so new. If you just took the warranty length of some lithium-ion batteries, could be 10 years, and you look at where lithium-ion batteries were 10 years ago, they really have no idea. And that's one of the good reasons why they have lithium-ion battery charging algorithms, that means the computer program, that can be updated as you're attaching to the internet. So they might figure out some way to charge and discharge your battery that's better, and then program your charger over the internet to make your batteries last longer. Sometimes you hear in the news about that car company. Try not to mention names too much because this is not an advertisement. But that car company that all of a sudden they update your battery and you have a longer range one day. Maybe they won't advertise it if your range is shorter though. Maybe they're being conservative in the first place and they figured out some fancy way of dealing with your batteries charging and discharging that's going to make that battery last longer. Kind of neat how that works. Let's talk about some different ways of charging and discharging these lithium-ion batteries. So first of all, we're going to talk about the constant current phase. In this way, the charger applies a constant current to the battery, and then the voltage expands until the voltage limit per cell is reached. So we have a constant current until we get to our voltage. So that's the constant current phase. You give it a constant current, Voltage goes up until your voltage is reached. In the balance phase, the charger decreases the current while the condition of the charge of the individual cells is conveyed to a similar level by adjusting the circuit until the point when the battery is adjusted. So that's also interesting too, that with some of these fancier energy storage system technologies, that you can adjust the voltage on a cell level. Amazing. One of the problems that sometimes people have with batteries, with all kinds of batteries, is let's say that you have batteries in series and parallel. We looked at some images of this, and one of the cells was worse than the others. So you can be overcharging a bad cell, and that can create problems. Now we're going to look at the constant voltage phase. In the constant voltage phase, we have a constant voltage equivalent to the greatest cell voltage, and then the current gradually decays towards zero until the current is beneath a set edge of around 3% of the steady current charge. So we start off with a constant current phase, we get up to our voltage, then we keep a constant voltage until our current goes down towards zero. Okay, now different advantages of lithium-ion batteries. So some of these advantages, we have a lighter design, so it's not as heavy, and that relates to our higher energy density. And so we have a high energy density. That means energy per volume. We have high specific energy, energy per weight. That's good for cars. Both of these things are good for energy storage systems and for everything. It's nice to have something that's light and small. Lithium being the lightest metal that there is, the third element on the periodic table. 3 protons, y'all. Lithium batteries by far have a lower self-discharge rate, so that would be a longer shelf life. You might remember back in the day when we were using different technologies that batteries would have this memory effect where you would have to fully discharge them, which wasn't too good for the battery. We don't have that with lithium batteries much, and it's all controlled with our electronics anyway in the battery management system. Lithium batteries are much better for quick charging and discharging than the lead acid batteries. They have a longer lifespan typically. Depends on how you treat them though, because some lead acid batteries can last for 15 years, and 15 years ago, people weren't using lithium batteries. Lithium batteries pretty much have low maintenance. I mean, it's like you can't do maintenance on them. In fact, your energy storage system that you buy is sealed in a container, and a lot of times any kind of maintenance is going to be done on a lithium battery. You have to have the factory do that. So you would have to take that energy storage system perhaps and send it to the factory. Just not a lot of maintenance to do on a lithium ion battery. However, if you had a utility scale energy storage system, of course there's going to be maintenance there. You're going to have to fix electronics, swap out some battery packs, things like that. And we have a high open circuit voltage for a lithium battery cell compared to the other technologies that we're using. Now we're going into these points a little bit deeper to reinforce them into your cerebrum. That's your brain, where you remember stuff. So lithium batteries are lighter compared to other rechargeable batteries, and that is important. Energy density is good. That's energy per volume. Good for stuff you stick in your pockets, and good for energy storage systems because they take up less space. When you put an energy storage system in your house, you mostly care about space more so than weight, because you're not going to be carrying it around. But it's nice to be lighter, especially if you're going to hang it on your wall, and especially for those guys that have to pick it up so they don't blow a disc and need back surgery. And then we're talking about specific energy here. That's energy per weight, and that's especially important for your vehicles. However, the mass production of batteries is based on specific energy because they're making most of these batteries for cars. So a lot of times when you're going to put something in your house, it's going to have high specific energy, which is, hey, high specific energy and high energy density all together, that's a great thing. And actually for all applications, it's good to have both. There's just some applications that it's more important. So cars, more important specific energy. And then for stationary batteries or things that you put in your pocket, your electronics, it's just not that much weight. And so you want high energy density. And also with lithium batteries, there's a low self-discharge. This is a great thing, especially if you're not going to be around much. And we can see 1.5% per month. Sometimes you see 3%. It would have to do with how you are making your battery, the design of it. But just in general, lithium-ion batteries have a very low self-discharge rate. I was talking to my brother recently, and he has a GPS device. He's a biologist, or I should say he has 2 GPS devices. One of them is his backup, and he always charges them together, and he noticed that the one that he uses, the battery is much better than the backup one, and that's because he is overcharging that backup device. because there's a very super low self-discharge rate, and then he plugs it in every time he plugs the other one in when he's going to use it, and then it gets overcharged and it's not good for the battery. So you remember those old batteries? We're talking about nickel metal hydride and things like that. So these nickel metal hydride batteries, in fact, that's what I have in my first generation Toyota Prius, which is almost a classic car by now, going on 20 years old. And I remember buying my first generation Prius brand new. It was a lot more expensive back then, state of the art. And now people say, what are you driving that old car for? Hey, I'm waiting for EV to grid. That's what I'm waiting for. Once these vehicle manufacturers open their minds and let me go and back up the house or go EV to grid, then I'm buying the electric vehicle. So it used to be with these nickel metal hydride batteries, if you wanted to have a lot of charge in there, you would have to drain it 100% and then charge it, because this battery had this battery memory effect. We pretty much ignore that with lithium-ion batteries. I remember when lithium first came out, a lot of people still thought we had that memory effect, and they were completely discharging their batteries, which was actually bad for the battery. So it worked against you instead of for you. So lithium batteries take less time to charge. They're quicker. There's less internal resistance. Other batteries like lead acid, nickel metal hydride, and NiCads, they charge a little bit slower. NiCads are not as good because of this toxic cadmium in there, so you don't see that as much. However, when they first put lithium-ion batteries on airplanes, there were some fires that we had in those beautiful 787 Dreamliners. So you still see NiCads in airplanes, because the main thing about an airplane is you have to be 100% reliable with all kinds of backup systems, because you don't want to fall out of the sky. It's probably a little bit better to have a little toxic cadmium there than it is to fall out of the sky, because falling out of the sky can even be more toxic. Lithium-ion batteries have a longer lifespan, and this is increasing as our technology gets better. So these numbers are constantly going up, but it also depends on how you treat your batteries. So they're going to design a battery for a cell phone to last for a year, because they want you to buy a new cell phone. They probably engineer it just so your battery wears out within a year or two when they're selling you a phone or a computer. But for a car, they want it to last a lot longer. Or for an energy storage system, they want it to last a lot longer, because nobody's going to buy an electric vehicle if their battery wore out in a year or two. So all of these things depend on how you take care of your batteries. A lot of times the warranty will include how you take care of your battery. And it's interesting to me how they do the warranties for the batteries, especially with electric vehicles, because that warranty is like for a gas car. It's for how many miles, or I should say distance, for those of you that like kilometers in different countries, or for a period of time. But perhaps they should have it for how many kilowatt hours go in and out of that battery, and how far you cycle it up and down, how fast you charge it. There's a lot of things that they could put in that warranty. They could put a lot of fine print there. However, the EV manufacturers, if they want to be in business for a while, they don't want to get the bad reputation and have people go, don't buy that car. I had to get a new battery every couple of years. That would not be good. Like we said, low maintenance. What are you going to do to maintain a lithium-ion battery? You're going to swap out the lithium? That's not going to happen. However, just like with lead-acid batteries, you can recycle them pretty easy. One thing about recycling lithium batteries, though, is don't put them in the batch with the lead-acid batteries. They grind up the lead-acid batteries, and they've been known to accidentally throw a lithium battery in with the lead-acid batteries, and it creates a nice 4th of July or New Year's Eve type of an experience. Kaboom! So our open circuit voltage is high, which leads us to have higher energy density and specific energy for a lithium-ion battery. Our open circuit voltage, our nominal voltage, all of our voltage is going to be higher than lead acid, nickel metal hydride, and NiCads. Okay, people, I hope you enjoyed this. I know there was a lot of terminology here. Some of it we've seen before, but we're looking at things from different angles, trying to get this into your memory. Thanks for listening to Sean White's Solar and Energy Storage Podcast. To find out more about everything solar and storage, go to Solar, SEAN. That's SolarSean.com. Over and out.